All right, guys, good afternoon. We're going to finish up our notes on S15 today, looking at the second of two existence theorem about the value of a derivative over a given interval. Rolle's theorem and mean value theorem guarantee that the derivative can take on a specific value, given some different criteria having been selected. Under Rolle's theorem, we guarantee the existence of a critical value. The derivative is equal to 0 so long as what has been satisfied. Derivative equals 0 on a particular interval so long as what is true. F of A and F of B are equal to each other. So the derivative is equal to 0 at some point between A and B, so long as the function is continuous on A to B, differentiable on A to B, and the left and right endpoints have the same value for the function. Right? So if I start hiking from a trailhead out in the mountains at an elevation of 8,000 feet, I go on a hike for a couple hours, and I come back to the same trailhead. I started and ended at the same elevation. Shouldn't I have maxed out or minned out my elevation at some point on my hike, for example? Mean value theorem is a similar existence theorem, except we're going to guarantee that the derivative is equal to the average value of the function for a particular interval. So in context here, I think I've said this before, takes me 2 hours to drive to Iowa City for a football game. Iowa City is 100 miles away. What was my average rate of change, my average speed? Miles an hour. That means that at some point, wouldn't I have had to have traveled exactly 50 miles an hour at some point during my trip?
Yes.
Because if I didn't travel 50 miles an hour on the average, how did I get there in 2 hours? If I didn't get up to 50 miles per hour at some point during the 2-hour drive, how did I get to Iowa City that fast? Or if my average speed was greater than 50 miles an hour, shouldn't I have gotten there sooner than 2 hours later? This pretty much is what the mean value theorem is trying to describe for us. So here is our mean value theorem statement. If function f is continuous on A to B, so it starts off with the same criteria. I have to have a continuous function on some interval. Our function is continuous and differentiable on A to B. And to have a smooth continuous curve. Then there is at least one C value in the interval A to B such that f prime of C, the derivative, is equal to the average rate of change, f of B minus f of A, all over B minus A. F of B minus f of A would be the average rate of change. Delta y, the total change vertically, is just the difference in f of b minus f of a. B minus a would be the change in x. So when I asked you what my average speed was, if it took me 2 hours to get to Iowa City, which is 100 miles away, didn't you just take 100 miles divided by 2 hours? That's essentially what you're doing here. The total change in distance divided by the total change in time. In terms of a function being graphed, it's f of b minus f of a divided by b minus a. I can graph that average rate of change by graphing the secant line between points on the curve. The slope of this line represents the average rate of change for our function on the interval from A to B. This is the secant line. The slope of the secant line is just that same delta y over delta x, which is f of b minus f of a over b minus a. That's the average rate of change for the function on the interval. At some points, it's steeper. Isn't the first part of the curve steeper the rate of change steeper on this part of the curve than the blue slope for our secant line? Sure. At some points it's shallower, it's less steep. This part of the curve, the rate of change would be less than the average. It's shallower, less steep than the slope of that secant line. But there is at least one point on our interval from A to B where the instantaneous rate of change, the slope of the tangent line, is the same as the slope of the secant line. There's at least one point on my trip to Iowa City where I wouldn't have traveled 50 miles an hour. Otherwise, how did I get there in that time? So I can graph that by kind of eyeballing where the tangent line would be parallel to the secant line. So I just kind of approximate with my ruler here. That right about there. Aren't those two lines pretty parallel for this point on my curve? So here's our first point. Call it C, maybe C sub 1. I think there's going to be another. Where the rate of change at precisely x equals C is the same as the average rate of change on the interval. Just do my best here to kind of approximate a tangent line. What do you notice about those two lines? They are what? I would have done my best to graph them. They're pretty parallel, and therefore they have the same slope. The average rate of change from A to B, this secant line here, is the same slope or same rate of change as our tangent line at x equals C sub 1. I believe I can find another point on the curve that would also have the same slope, the same rate of change as the average. Wouldn't it be right about here? So let's call this C sub 2. The tangent line at this point has the same slope as the secant line graphed between the points A and B. Therefore, the average rate of change from our secant line is the same as the instantaneous rate of change, the value of the derivative at x equals C sub 2. F prime of C sub 1 is the same as F prime of C sub 2, which is the same as F of B minus F of A all over B minus A. Here is our tangent line. The slope of the tangent line is the same as the value of the derivative at that point C sub 1. So what I was trying to sketch, at least my best, is what I have on this GeoGebra applet on the television screen right now. What we have modeled here on the screen is our function f, this blue curve, left to right. The secant line in green represents the average rate of change on the interval A to B. Slope of that secant line represents the average rate of change in the function from A to B. There is some point C between A and B where the tangent line in red would be parallel to the secant line, and therefore the instantaneous rate of change at that point would be equivalent to the average rate of change for the function on the interval. So if I slide point C from left to right, eventually those two slopes, the one in red and the one in green, should be the same. Right about there. For some points on the function from A to B, The function's steeper. Its instantaneous rate of change is greater than the average rate of change. At some points on the curve from A to B, it's shallower, it's less steep than the average rate of change. But wouldn't I, at some point, have to be equal to the average rate of change? Otherwise, how did I get there from one point to the other, given that distance? That would be right about there. That makes sense so far? Everybody online, did I get that explained okay? Questions so far? The reasoning behind mean value theorem? Okay. Let's see this in context. I've got a couple different functions and an interval. Let's make sure that mean value theorem applies, and then find such c-values guaranteed by mean value theorem. Find the points on the curve where the average rate of change is equal to the instantaneous rate of change at our given point. So a couple of scenarios here. For the first one, find all values guaranteed by mean value theorem, MVT, for a function f of x equals 5 minus 4 over x on the interval from 1 to 4. So is f of x continuous on 1 to 4? Let's check that first. Let's make sure that these criteria have been met. Because like we saw yesterday, a sample question might be, why does mean value theorem or why does rules theorem not apply? So which criteria was not met? Let's see if this one actually applies here in our specific case. Where is 5 minus 4 over x discontinuous? Where is it not defined for a given x value? Is in there. Where is this function discontinuous? Why? Can't divide by 0. If x is 0, 5 minus 4 over 0 is not defined. But is 0 a part of the interval? No. So that's no big deal. Should be continuous on 1 to 4. I also believe that it's a smooth curve. It's differentiable. There's no corner points or vertical tangent lines from 1 to 4. So it's also differentiable. Let's now find the average rate of change. Let's find f of b. Let's put that right here. Minus f of a divided by b minus a. What are a and b in this context? Get that shoved over here. There we go. A and b are what two numbers? Second check. 1 and 4. So I'll replace the b's with 4, and a's with 1. F of 4 would be 5 minus 4 divided by 4. 4 divided by 4 is 1, so 5 minus 1 is 4. F of 1, 5 minus 4 divided by 1. 4 divided by 1 would be 4, and 5 minus 4 is also 1. At x equals 4, my function has a value of 4. At x equals 1, my function has a value of 1. So the total change in y would be the difference in the two. 4 minus 1, the total change in x would be 3. 4 minus 1 is 3. 3 divided by 3 would be 1. The average rate of change on our function within the interval would just be 1. Now let's find f prime of c. Let's get a formula for the instantaneous rate of change for any c value between our interval from 1 to 4, between a and b from 1 to 4. Maybe think of 5 minus 4 over x as 5 minus 4x to the negative first, and now we can apply power rule. What's the derivative of 5, the first term? 0. How about the next term? What's the derivative of negative 4x to the negative first? What do you do with the negative 1? Okay, I'll bring down the negative 4, I guess, to get started with. Use the power rule. The derivative of x to the negative first would be negative x to the negative second. I bring down the power, and I replace the exponent with 1 less than it was previously. Multiply my two constants together. Actually, this should be in terms of c. Pardon me. Negative c to the negative second. Multiply the two constants together, and it's positive 4. C to the negative second, I'll put on the bottom. 4 over c squared. Mean value theorem says there's at least one point on the interval from 1 to 4 where these two things are equal to each other, where 4 over c squared, the instantaneous rate of change, is equal to 1, the average rate of change. And we simply just solve for c. C4 equals c squared. I multiply by c squared to both left and right. Take square roots. And c equals plus or minus 2, but we don't need the negative 2. So I think we're good. Should just be positive 2. For a c value of 2, the rate of change at x equals 2 is equal to the average rate of change on the interval. Let me graph the function on Desmos. 5 minus 4 over x. We're going to restrict our settings to be along the x-axis from 1 to 4. So I have the appropriate viewing window, given the interval we had in the question. Let's maybe see y from 0 to, how about 0 to 6? That should just about do it. I once again use my ruler here to approximate the secant line and tangent line. The secant line, or our left and right endpoint, has the same rate of change, has the same slope as the tangent line at x equals 2. Notice that I have a smooth continuous curve from left to right, so I was able to find and apply mean value theorem to find our answer of 2. Anything so far, guys? Let's try one more. Same setup, same question, new function, new interval. Find all values guaranteed by mean value theorem for f of x equals the function the square root of x minus 3 on the interval from 7 to 12. Find all values guaranteed by mean value theorem for function f of x equals square root of x minus 3 on the interval from 7 to 12. Let's first make sure that MVT applies. Is our function continuous for x values between 7 and 12? For what values of x would my function not exist? Just like this first function didn't exist when x is 0. What values of x are not a part of the domain of the square root of x minus 3. What values make the square root of x minus 3 not a real number? Can't divide by 0. What can't you take the square root of? What types of numbers can you not take the square root of as a real value? Negative. So where is x minus 3 going to be negative? What values of x make x minus 3 a negative number? Or anything less than 3, right? If x is less than 3, then wouldn't x minus 3 be a negative value? Is that a problem, though? Look at your interval. 7 to 12. So is that going to be an issue? I think we're good to go here. Should be differentiable on that same interval. Corner points, cusps, vertical tangent lines, asymptotes, discontinuities, etc. So we can apply mean value theorem because I have a smooth, differentiable, continuous curve for a function f of x on the interval from 7 to 12. Let's find the average rate of change. What is f of 12? Minus f of 7. Divided by 12, minus 7. Well, f of 12, what's 12 minus 3? What's the square root of 9? F of 7, do the same thing. What's 7 minus 3? 4. Square root of 4 should be? Total change in x from 7 to 12. Sorry, total change in y from x equals 7 to 12 is 3 minus 2 or 1. The total change in x would be 12 minus 7, which is average rate of change is therefore 1/5. Y changed by 1, x changed by 5. Let's find f prime of c to describe the instantaneous rate of change. Maybe think of the square root of x minus 3 as x minus 3 to the 1/2, and now I can use chain rule, power rule again. All right, one more time. What do I do with the 1/2 to take the derivative? Up to the front. So we'll have 1/2 times c minus 3 to the negative 1/2. If the inner function had a derivative that wasn't already 1, I'd also need to multiply by that. But c minus 3, the derivative should just be 1, so we don't need to worry about it. Let's see here. I'm going to clean this up by moving that negative exponent back down to the bottom. 1 over 2 root c minus 3 for our final derivative. MVT says there's at least one c value where these two are equal. The average rate of change of 1/5 and the instantaneous rate of change given by this derivative are equivalent to each other. So where is 1 over 2 root c minus 3 equal to 1/5? How can I start solving for c? What can I do with this proportion? Cross products, you bet. Cross them up. 5 times 1. 2 root c minus 3 times 1. So that's just going to be 2 root c minus 3 equal to 5. Divide both sides by 2. Square roots of c minus 3 equals 5/2. Square each side. That should give me c minus 3. What's 5/2 squared? 5 halves times 5 halves. Yeah. Add 3 to each side, so C equals 25 fourths plus 3, which is 25 fourths plus 12 fourths, or 37. What is that as a decimal? 4 divides into 37 9 times with 1 left over. So 9 1/4, 9.25. That's in the interval. That's in the interval from 7 to 12, so I think we're all squared up there too. Share this back again. Our function was the square root of x minus 3 along the interval from 7 to 12. Go from about 0 to 4, the y-axis. As you can see, just, it's almost a straight line because of the limits here, but the average rate of change, the secant line connecting the left and right endpoints, is the same as the instantaneous rate of change. I slide this up to the tangent line at about 9.25, roughly